In this video, we are going to show that the expectation of the sample variance is equal to sigma square. Well, the sample variance is equal to the summation from I to n of xi minus x bar and square divided by n minus 1. We can move n minus 1 to the left side, and we get the square, the summation of the square, which equals to xi minus mu plus mu minus x bar. We are sticking in minus mu and plus mu, which sum up to be 0. So this doesn't change the result. Once we have the minus mu and positive mu, we could start to square it. This is turned out to be in the first term, and the twice of first and second term plus the square of the third term. Now we can start to well, first of all, when we multiply this term to this term, actually we could switch in the order, which gives you mu minus x bar, and we take out the minus sign over to here. That's why we get a negative 2. And now we could distribute the summation to the first term, and to the second term. We are sticking the summation in for this factor. And here the summation of this term is equal to n times mu minus x bar square, because if we expand this is going to be mu minus x bar square plus mu minus x bar square. So there are n terms here. So if we sum them up, it will be n times mu minus x bar square. Now, regarding this term, if we expand this, it will be x1 minus mu plus x2 minus mu plus x3 minus mu plus etc. until xn minus mu. And if we group them together, it will be x1 plus x2 plus until xn. And since there are n of minus mu's, that's why we have minus n times mu, which is here. And if we take out n, we factor out n, this gives x bar minus mu. Now 2 times n gives 2n, and this x bar minus mu times x bar minus mu is becoming the square. So up to here we have minus 2n times that plus 1n times that. If we add these two terms together, this will give minus n times x bar minus mu to the square. So now we start looking at the proof. E to the s square is equal to this, which is just from the expansion from this square term, and n minus 1 remains the same. We pull over the n minus 1 to the left side. Now this gives the product of this is equal to, if we distribute the expectations, and if we expand this term, it gives expectation of x1 minus mu square plus x2 minus mu square, etc. until expectation of xn minus mu square. This term is just by moving n outside of the parenthesis. That's the definition of expectation calculation. And expectation of x1 minus mu is just the same as expectation of x minus mu squared, because x1, xn, and x2 and xn, they are all having the same distribution as x. So we have expectation of x minus mu to the square n of them. That's why here we multiply by an n. So these terms eventually becoming n times that number. And this, we just copy that down. Notice that variance of x is by definition equal to this as well as this, but we only need this part. And that's why we can substitute variance x for this equation, for this expression. It gives n times variance of x. And for the same reason, this is going to be the variance of x bar. Now, since variance of x is defined to be sigma squared, we can substitute that, and variance of x bar is sigma squared divided by n. Now, n cancels with n, gives sigma squared, which gives you n minus 1 times sigma squared. And this n minus 1 cancels with n minus 1 over here. This, and then eventually gives expectation of s squared equals sigma squared.